Hi everyone, welcome to the fourth lecture of the summer preparation series on probability for the data analysis course. Today we will talk about disjoint and independent events. We have been talking about disjoint events in our last lecture, so today we'll do a review and then we'll contrast it with independent events. Disjoint events are basically mutually exclusive, like what we have seen in the last lecture. And let's just go into a little bit more detail about this idea. Mutually exclusive events are basically events that prevent each other from happening. So when event X happens, event Y should not be happening, and vice versa. So let's look at an example. If we conduct an experiment where we pick a car at random, will this car be both green and white? Because we know that cars usually only have a single color, it's either a green car or a white car. Usually a car does not have two colors. So we can say that if that's the case, of course there may be exceptions to this rule, but if this rule is correct, then we can say that these are two mutually exclusive events. That being green excludes the event of being white, and being white excludes the event of being green. We can say that these two events, being green versus being white, are disjoint events. They are mutually exclusive. In other words, the intersection between the two, the probability of green intersecting with white would be actually 0, because that would never happen. So you can see that in a Venn diagram that illustrates disjoint events will have two circles that do not overlap with each other. The intersection is the overlapping portion. So when there's no overlap, we know that these two events are mutually exclusive. Here's another one. If we roll dice, will this outcome be both 2 and 3? So again, from experience and knowledge about dice in general, we know that it's impossible to roll dice and get both 2 and 3. So when we get 2, the event of getting a 2 will prevent the event of 3 from happening, and vice versa. So again, we call these mutually exclusive events. There's no intersection between the two, so when you have the two circles, they would not overlap with each other. The intersection will be 0. Let's take a look at the implication for the multiplication rule. So usually the intersection, from last lecture, we know that the multiplication rule is about calculating the intersection between two events. And the equation for the intersection, the multiplication rule, is basically the probability of x given y multiplied by y. And that's how we would be able to estimate the intersection between x and y. However, in the event of mutual exclusivity, there's no intersection. Okay, so this is 0. And we know that P of y, the probability of the event y, is probably not 0, because it's just a regular event. That is not the probability of y is not affected by mutual exclusivity at all. So that number will remain whatever it is. And so for this equation to work, we know that the probability of x given y has to be 0 in order for the intersection to be 0. In other words, when you see mutually exclusive events, you know that the probability of x given y should be 0, which makes sense, right? So what's the probability of the event x happening, given that we know the event y has already happened? Well, the answer is 0, because that's just the basic definition of mutual exclusivity, right? Event X should exclude the happening of event Y and vice versa. And we know that the reverse should be true. So the probability of Y given X should also be 0. Let's look at union. So what about the union of the two, right? So X or Y, what's the probability of these mutually exclusive events happening? And we want to look at the union of the two. Well, this addition rule applies here. And because we know that X intersection Y is 0, then we know that the union of the two will simply be X probability of X plus probability of Y. So this is the additional rule from last lecture. So let's look at this example. So we have rolling the dice of 2, rolling the dice of 3. And if we want to know what's the probability of getting either a 2 or a 3, because these are mutually exclusive events, we can just add them up. So the probability of getting either will be 2 divided by 6. Let's take a look at this. Real world, real example, no longer rolling a dice. What's the probability that a baby is both boy and girl? Well, we know that, gender is a complicated thing, and it is possible to have both a boy and a girl, but it's very, very rare, and the chances close to 0, not 0, but pretty close to 0. So in this case, we'll say, for the most part, being a boy versus being a girl are primarily mutually exclusive events, typically. So I want to say that there are always exceptions to the rule, but predominantly we can consider them in the majority of the cases that they're mutually exclusive events. So what's the probability that we will get a baby that is both boy and girl? Well, being a boy usually prevents you from being a girl, and vice versa. So the intersection of the two should be close to 0. In other words, the probability of being both a boy and a girl should be close to 0. But again, I want to emphasize that, things do happen, and there are always exceptions to this general rule. Now let's take a look at independent events. And independent events, when we talk about this, we often will say, assuming that, X is independent of Y. We'll see this a lot in our data analysis course. A lot of the analysis assume independence, so this will come up very frequently. So it's very important that you have a solid understanding of this concept. Okay, so independent events does not, this idea does not mean that X prevents Y from happening or Y prevents X from happening, and that is the idea of mutual exclusivity. Okay, the idea here is that X and Y can happen at the same time, and however, the probability of X does not affect the probability of Y. And we'll elaborate on what that means. Okay, so the idea is that disjoint events are very different from independent events. You want to remember that. And then hopefully the rest of the lecture will elaborate on the reason why these two are different. And you need to be able to recognize the differences. Okay. So these are two events. Okay, experiment when we roll dice twice. Okay, so what's the probability that the first roll is a 2 and the second roll is a 3? Okay, so now you can see this is a series of events. We have the first event, and then the second event happens after the first event has happened. Okay, so this is very different from the single roll that we saw in the discussion of mutual exclusivity. So I want you to take a note of that. These two events are what we call independent events, in the sense that whatever result that you get in your first roll will not affect the outcome of the second roll. The probability of getting a 2 in the first roll is 1/6. However, after that, your second roll is still fair game. You still get 1/6 for every number. Whatever you get in the second roll has nothing to do with the first roll. Independent events are unrelated events. So X and Y are unrelated to each other. The probability of X does not depend on probability of Y. So whether Y happens or not has nothing to do with it. It will not affect whether X will happen or not. The probability of Y does not affect the probability of X at all. So these two, when events are independent, that's what this means. Okay, so they can still have overlap. So you can see they're not mutually exclusive. They can have overlap. However, their probabilities do not affect each other. So we say that X is independent of Y when the probability of X given Y is X. Because whether X happen or not, well, whether Y happens or not, the probability of X will just be X. Because X is unrelated to Y. So whether Y happened or not, the probability of X will remain X. So, when we translate that into the mathematical notation, this is what happens. And if we think about the multiplication rule, which applies to the intersection right here, the intersection is the multiplication of probability of X given Y and the probability of Y. Now we know from the first statement that the probability of X given Y is basically P of X. Then we can rewrite the statement as P of X multiplied by P of Y. So the intersection of X and Y is now simply X multiplied by Y. Okay, this is very important. We will be using this again a lot, and actually this equation a lot in our data analysis course. So this is what the intersection is. X times Y is when these two events are independent, we can simply multiply them, but in order to get the intersection. Like I said, independent events are not mutually exclusive. Independent events, the overlap over here, the intersection will be probability of X times probability of Y. When you have mutually exclusive events, the intersection will be 0. Now, let's look at the baby example again. What's the probability that both baby number 1 and baby number 2 are girls? So if we have 2 pregnancies in a row, what's the probability that the first baby is a girl? And then again, we get another girl. Okay. The probability of getting a girl is roughly 50% based on years of experience, right? Thousands of experience that we know about pregnancies. We know roughly 50% of the pregnancies are girls and roughly half of them are boys. So the probability of getting the first baby as a girl is 0.5. But the second one is also 0.5. So whether the first baby is a girl or a boy will not affect the gender of the second baby at all. So every pregnancy is a new gamble, basically. They're relatively independent. They're basically independent events. And again, how do we know that? Well, we know that from thousands of experience. We have made lots and lots of observations, and biologists have already made the estimations. They have lots and lots of evidence that these events are unrelated to each other. So these are independent events. Probability is always 0.5. And so if we want to have the probability that the first one is a girl and the second one is a girl, we're looking at the intersection of the two, then we basically multiply them based on the rule that we just derived on the last slide. So 0.5 times 0.5 will be 0.25. So it's a 25% chance to get two girls in a row. Now, here's another example. Firm A has 10 employees, 3 women and 7 men. They are trying to promote 2 of them to VP positions. What's the probability that both of them are women? Now, I want you to take a moment to think about this and see how this is different from the pregnancy example. Okay. Specifically, I want you to think about whether these 2 VP promotions, are they mutually exclusive or are they independent? Okay, so let's have like 2 slots for these 2 promotions. And let's think about the probability of getting a woman for the first promotion and then the probability of getting a woman for the second promotion. And then that's how we can calculate the probability of both, right? So, after we do these 2 separately, and then we can look at the intersection. So the probability of the first VP of being a woman would be 3 out of 10 because they have 10 employees and 3 of them are women. So 3 out of 10 or 30% chance that the first one will be a woman. Okay, so we put the 0.3 in the VP1 position. However, let's think about the second one. Okay, what's the probability that we will get a woman for the second position, given that the first one is already a woman? Okay, well, the probability for the second promotion will actually no longer be 0.3 because a woman has already been taken out of the game because the first position takes away 1 woman already, 1 woman candidate. So now we only have 2 women candidates available, and the entire pool will only be 9, not 10 employees. Okay, so hopefully you can see that the probability of the second VP promotion now has changed from 0.3 because of VP1. In other words, these 2 events actually affect each other. The probability of the first one, whatever happens with the first one, will actually change or determine the probability of the second one. In other words, the probability of VP2 actually depends on VP1, and therefore these 2 things are dependent of each other. They're no longer independent of each other. Sometimes we call this basically, if you're talking about drawing a card, playing a card game, in sort of traditional probability discussions, people will say that this is basically drawing a card without placement. So you hear that a lot. I tend not to talk about the replacement, with replacement, without replacement. However, I want you to recognize this phrase. Whenever you see without replacement, that means that these events are actually dependent of each other. So because we have taken 1 woman out to fulfill the first VP position, we are not replacing the employee pool. That's basically what this phrase is about. Okay, so instead of bringing on another employee, we not only have 9, we're missing 1. We're down by 1 employee, so the pool is shrinking, and we're not replacing that empty spot. Okay, So that's why the probability of the second promotion will depend on the first promotion. So now the second one, being a woman, will only be 2 out of 9, okay, instead of 3 out of 10, and that's a 22% chance for the second one to be a woman. So that's the second position. And therefore, the probability of number 2 depends on probability of number 1, and this is where we call these dependent events. They're not independent of each other. So this is very different from the pregnancies, where the probability remains 0.5 for it remains constant for every pregnancy. Here, with every successive promotion, the probability changes. So in order to calculate the probability that both VP promotions are women, we are looking at the intersection between the two probabilities. And because these are dependent, they're not independent of each other, right? So these are not mutually exclusive, because when both of them can happen, they don't exclude each other. However, they're no longer independent events. So in order to calculate the intersection between the two, we will have to calculate the updated probability. Now, the second one is an updated probability of 0.22. It's no longer 0.3. So now these two events, because we already adjusted the second probability, we can treat them as independent events. So when we're looking at the intersection, we can, again, multiply the two of them. So 0.3 multiplied by 0.22, which is 6%. So to summarize and to contrast the differences here, independence is really about replacement. So if you get a baby girl, but then you don't take a girl chance away, right? Then the second game is still fair game. You haven't affected the probability, you haven't affected the pool at all. Then we can consider these as independent events, or what we call with replacement in traditional probability. Now, if you promote a woman for the first VP position and you take that woman out of the sample space or the pool, then you're sort of affecting the probability of the entire pool, right, for a promotion. And so the second one depends on the first one. This is what we call without replacement. And then you're creating these dependent events. And that's it. So hopefully this lecture clarifies the ideas of mutual exclusivity versus independence. I encourage you to do more practices on Khan Academy. By going to the website under Lecture 4, Independence, you should be able to see more practices listed under Lecture 4. There's also a quiz, so you can complete these practices to make sure that you have a full understanding of these ideas. So to summarize, what did we learn today? We learned about mutual exclusivity. We also learned about independence. We learned that the intersection for mutual exclusivity is 0, but for independence is the multiplication of probability of X and probability of Y. In mutually exclusive events, the probability of X given Y will be 0, but in independent events, the probability of X given Y will be probability of X. When we look at union, mutually exclusive events can, the union will be just the two pies added up together. So probability of X and probability of Y added up together. There's no intersection, so it'll be minus 0 or nothing. Independent events, on the other hand, will be the probability of X plus the probability of Y, and then you have to subtract the intersection right here. And the intersection is probability of X and probability of Y. So this right here is the intersection. Any questions? Feel free to contact me at rachel.chong@mason.wm.edu. I'm happy to chat over Zoom or over the phone, answer any questions you may have. Thank you very much. See you next time.